Okay, so we just finished the acid-catalyzed hydration. Now we're going on to oxymercuration, demercuration, hydroboration, oxidation, catalytic hydrogenation, halogenation, and halohydrin formation. So you're going to see some similarities between oxymercuration and hydroboration. You're not going to see you're going to see some similarities between halogenation and the reactions that we just finished covering earlier that go through the carbocation intermediate. So let's go on to these and I'll point out the similarities. But again, it's very important that you pay attention to the mechanisms because it will help you to group these things together. And you can go back and look again at these summary videos that I've created for you using the overhead camera, the document camera, and those videos summarize all of these mechanisms. And if you go through those as if you keep going back and looking at those summaries as you complete each of these, it will really help you remember them if you are constantly paying attention to the similarities and differences. So oxymercuration, demercuration. So oxymercuration is called oxymercuration because across the double bond you attach oxygen and mercury. And so then the demercuration is where you remove the mercury functional group. And so the overall effect is that you're generating an alcohol. Now compare this to the acid-catalyzed hydration. So with the acid-catalyzed hydration, you would first attach a proton to the double bond. The proton would be attached here at the terminus, the terminal carbon, and then the positive charge would be generated at the internal carbon, and then the water molecule would come in and attack at the site of the positive charge. So you would get this exact same alcohol functionality, this exact same alcohol molecule, the product. Okay, so you're getting the Markovnikov product. This is the same product as you obtain in acid-catalyzed hydration. But the difference is the acid-catalyzed hydration goes through a truly free carbocation, and this does not. And that becomes important because the truly free carbocation can rearrange, and this will not. So you can prevent rearrangement by going through oxymercuration, demercuration, instead of the acid-catalyzed hydration. Okay, so that's what made this reaction valuable. That's the benefit of this reaction. No rearrangement of the carbon skeleton. So here we are. So you have the mercuric acetate. This is what you're going to use to effect the oxymercuration, demercuration. And so the first thing that happens is acetate departs and you have the mercuric cation. So here you have mercury bearing a positive charge. Notice this, you have, so this mercury is typically divalent. Okay, so this is not a mercuronium ion. Mercury, in order to have mercuronium, you need to have a trivalent mercury. Okay, so you haven't gotten to mercuronium yet. Okay, so the first thing that happens is you lose acetate. And so now you have a mercuric cation. This could also be called a mercurinium cation, okay? But that doesn't matter. That's unimportant. So what happens is, this is the typical, this is what you would have when you have the typical acid-catalyzed hydration. This is not what you get from oxymercuration. This is what you get. This is the mechanism for oxymercuration. So notice that the mercury comes in and near the pi bond, and the pi electrons attack the mercury cation. Okay, and notice that this is a resonance structure. This is a resonance structure. And so the actual molecule that's formed here, the intermediate that's formed here, has, it's a three-centered intermediate. So it has, it's bonded to both carbons. This one carbon is just really sort of a partial bond, but it's enough of a bond to keep the thing from rearranging. Okay? And so remember that. This is a resonance structure. You have a full bond and a partial bond. Full bond and a partial bond. Both of these structures are resonance contributors to the actual structure of the intermediate. So this will not rearrange. In other words, you will not have free rotation about this carbon-carbon single bond. Okay, there's enough of a bond, enough of an association here to prevent any sort of rearrangement or rotation. And so now, here it is. This is the way that this is drawn. You have a full bond and a partial bond. And then the nucleophile comes in to attack. It's sort of like an SN2 rearrangement or SN2 reaction, where this has to come in from and do a backside attack. It's not going to come in over here from the front side. It's blocked by mercury. It's going to come in from the backside. It's like an SN2 reaction. And so then the nucleophile is attached and the mercury has just simply moved over a little. Okay, so now you have a full bond to this one carbon, and now you have no bond at all to the other carbon because the attack by the nucleophile has displaced the mercury. Okay, and then sodium borohydride is used to replace mercury here. So this becomes CH. This becomes CH instead of CHG. This donates H minus, and you get hydrogen here. Okay, and I'm not going to go into the mechanism of that. It's sort of complicated, and so you won't need to know the mechanism. Just remember that this donates a hydrogen to replace the mercury here. This is hydrogen rich, and so that should be something that's easy for you to remember. So now, the two reactions here with you, when you have, this is to make the point again, when you have acid-catalyzed hydration, you can have the reaction occur without rearrangement or with rearrangement. Okay, and if this is the desired alcohol, you're going to lose some of your reactant by getting this undesired product. However, if you use oxymercuration, so if you use oxymercuration where you have, here's the mercury, and then this is the nucleophile. So let me back up. Here is the nucleophile, so this would be the water coming in for attack. This would be water coming in for attack. See the water here? This is the nucleophile. So you have the mercury become attached. It will become attached to the terminal carbon, and then the nucleophile oxygen comes in and attacks, and then the carbon-mercury bond is replaced by a carbon-hydrogen bond, and so now there is no rearrangement, and you get only the desired alcohol, and so this is the benefit of oxymercuration. You get no rearrangement. So another way to synthesize alcohols, you can see we're sort of marching down through the syntheses of alcohols. So another way to synthesize alcohols is hydroboration oxidation. So we've had catalytic hydrogenation to give the Markovnikov product. We've had oxymercuration, demercuration to give the Markovnikov product with no rearrangement. And now you're going to have hydroboration oxidation to give the anti-Markovnikov product. So you've got 3 different syntheses of alcohols to give you 3 different procedures that have different synthetic uses. They're valuable differently in synthesis. Okay, so here is the, let me just start out by saying that hydroboration is governed very much by steric effects. Okay, and so what happens is when you have hydroboration, you're going to have hydrogen and boron added across the double bond. That's why it's called hydroboration, because you're going to have hydrogen and boron added across the double bond. And so the boron is going to become attached to the less sterically hindered end. Hydrogen will go in here. Boron will go here. And then this next step, the oxidation step, the carbon-boron bond is replaced by a carbon-oxygen bond. That's why it's called oxidation. So the first step is to form a carbon-boron bond, and then the boron is replaced by oxygen. And so now you've attached oxygen to the terminus of the carbon chain. Okay? And in the other 2 syntheses, we were always putting oxygen on the internal position. Now you put it on the terminal position. So this is something different and valuable synthetically. So hydroboration followed by oxidation due to hydrogen peroxide and sodium hydroxide. So let's look at this. This is stereoselective. Hydrogen and OH are added in a syn fashion. Now that's a very simple statement, but it's more complicated than that. So the first step, hydroboration, what you get is the boron and hydrogen are added from the same side of the molecule. Always. You always have a syn addition. Okay? And then when you have oxidation comes in, the oxygen replaces boron, and there's no rearrangement. So you have HBr, hydrogen and boron attached. The boron goes here. Remember, the boron always attaches to the less sterically hindered end of the double bond. So you have hydrogen and boron, and then in the second step, you're going to have oxygen replace boron. Okay, so it's going to be syn addition. And it can happen from one side of the molecule, it can happen from the front, or it could happen from the back. And that is what determines. Here it's happened from the front, here it's come in from the underside of the molecule. So these are the 2 possible enantiomers, and anytime that you have a planar molecule or intermediate and it reacts, you're going to have a possibility of your reactants coming in from one side or the other. And in my opinion, there's no need to keep making such a big thing of it. The reactants the reagents can come in from one side or the other. And if you have a planar reactant, that's the case. If you have a planar carbocation, it's the same thing. If you have something planar, react with some reagents, they can come in from either side. And I think that's a pretty simple concept. The important thing is that anti-addition is not observed ever, 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 ever in hydroboration, ever. Okay, no anti-addition in hydroboration, ever. So here, the point is made that it's the same situation if you have a planar carbocation intermediate, or well, here that it's not. This is not. Here you have an empty p orbital on a carbocation intermediate, and boron has an empty p orbital on it. So BH3 is planar. I don't know if that is so important, but it's a good thing to remember. So boron has an empty p orbital. So here, the actual form that boron takes when it reacts is as diborane. So it's actually B2H6, and these are very unusual orbitals. It is a three-centered orbital with 2 electrons in it. Okay, and it's very unusual. You would not want to draw that in a whole lot of different molecules. Okay, and this is probably the only one that you're going to see in this textbook, where you have a three-centered intermediate, a three-centered orbital with just two electrons in it. So it's 2 electrons spread out over 3 atoms, and you've got it above and also below. So this is one molecule. It's a dimer. And so you could also draw it like this, where, again, these are 2 different resonance contributors. They contribute equal amounts. This is, I think, a better picture of it, of the actual molecule. And then it is known, though, that when it goes into react, that the dimer, just before it reacts, separates into the 2 monomers, just before it reacts. When it undergoes the reaction, it separates. Okay? It does not react as the dimer. So, another form that borane is used in to react is when it's complex with THF. So borane THF, borohydride along with THF. So what's happening here is the lone pair is complexing with boron. This lone pair is being donated into the empty p orbital, and when the pair of electrons is donated from oxygen onto boron, that means that the oxygen is going to bear a positive charge and boron is going to bear a negative charge, because this bond that's formed is using a pair of electrons from oxygen, and boron is receiving that lone pair into its empty orbital. And so this is a very common way to effect, or it's a very common reagent that's used to effect hydroboration. This is very common. Okay, so hydroboration, this is what I was telling you about. So what happens is, notice that when you have BH3 come in to react with the double bond, the boron is attracted to the less sterically hindered end, because you've got some sterics here, and as it reacts, you're going to have a partial positive charge generated here at this carbon, and each of these 3 hydrogens are bearing a partial negative charge, because boron is sort of like a metal, and so it's donating its electron density onto the hydrogens. So this is really partial minus, partial negative, and so the partial negative is attracted to the partial positive, and so the boron comes in. There's electronic effects as well as steric effects that govern the reaction here to put boron at the end of the double bond, and the hydrogen is added to the internal position. But notice, this is transition state, and notice you have a 4-centered intermediate. This is a 4-centered intermediate. Hence, the boron and hydrogen must be added from the same side. You must have a syn addition. Anti-addition is not possible. And so, it's not shown here, but you do have the syn addition. Here, you can see once again the boron is going to the less sterically hindered end, and once that reaction takes place, just like it's shown up here, you still have 2 active BH bonds that can still affect hydroboration. And so here you can see after the first addition, you still have 2 active BH bonds that can do that same reaction again to 2 other alkenes. This one can react with an alkene, and this one can react with an alkene. And as they react, the steric hindrance about boron increases. And so you wind up with 3 alkyl groups on boron, so it's called a trialkyl borane. This would be a monoalkyl borane. After the next addition, it's the dialkyl borane. This is a trialkyl borane. And so there are 3 active BH bonds in borane. The more substituted carbon will be better at stabilizing a positive charge. Yes. So, we've already seen that. We've already discussed that. This is just a better drawing. It shows the steric hindrance a little bit better, and shows the boron being attached to the terminal carbon and the hydrogen going to the internal carbon. If you had it the other way, you don't have this. It's showing what you don't get here and why you don't get it, because you have more steric hindrance. It's more crowded. And so this is why you get anti-Markovnikov addition, because the boron is going to the terminal carbon, and then the boron will be replaced by oxygen in the oxidation step. And so that is what leads to the anti-Markovnikov product. This you do not obtain. You do not obtain the Markovnikov addition or the Markovnikov product in this reaction, in hydroboration oxidation. Now, I want to go back to the terminology stereospecific versus stereoselective. This is pulling this out of another chapter, out of chapter 7, and you notice we're in chapter 8, but I wanted to go over this again because I think that the textbook is glossing over this just a little bit. I don't think it's explained well at all in your textbook, and this is a little bit of a difficult concept to explain. So, if you, once again, the difference between stereoselectivity and stereospecificity is in stereospecificity, it has to have been shown that if you have 2 different stereoisomers and you react them with the same reagent, you get 2 different products, which are stereoisomers. Now, let's go back to hydroboration. So, here, notice I said that you will get, here, because of this, you will get syn addition, and you will get only the one product. It is not possible to get anti-addition. Okay? You can't switch this around somehow, go to another reactant and get anti-addition. You can never get the other product. This will give you a very specific, a very stereospecific product, but you can never get the other one. You can't have the pair of reactants. Okay? You will only be able to get the one. And so that means that hydroboration is stereoselective because you only have one possible reaction. You can't use two different reactants and get two different products. So you can't have the pair here to demonstrate. So hydroboration is called stereoselective because you can start with one and you can get only one. Here it doesn't have to be major and minor. It can be one leads only to one. But if you don't have the other one leading to the other one, if you can't demonstrate that you have the pair leading a pair of reactants, leading to a pair of products, it's not stereospecific. Remember what I told you about the P? The P is for pair. And so we're going to see other examples of this. And as a matter of fact, in your textbook, it isn't explained clearly at all. So hydroboration is stereoselective. Okay? Only syn addition occurs. Yes, there's one chirality center, but that doesn't matter. That's not what is important in this reaction. You'll see what's important later, and I will point it out to you. So a mistake in the textbook is here. Syn addition is possible. Anti-addition is not. Okay, because of that force-centered transition state. That's the key to everything, the force-centered transition state. And that's very unusual to have a force-centered transition state like that. So there's not a pair of enantiomeric reactants giving a pair of enantiomeric products. The reaction is not stereospecific. Hydroboration is not stereospecific. Hydroboration is stereoselective. Okay? And there's a lot of discussion about this in your textbook and trying to say whether it's stereospecific or not. It doesn't matter. None of this matters. That's not what is the criterion. That's not the criterion for stereospecific or stereoselective. Anytime that you have a planar reactant, you can always have the reagents come in from the top or the bottom. That's very common. And that is not a determinant for stereoselectivity or stereospecificity. Ever. So here, I have put this in. This slide, none of this is going to be present in your textbook. This, I think, tells you better than anything. So here are a couple of enantiomers. Okay, and here they are in the bond line notation. So here you can see this is the same as that. Okay, these are the same, except these are just showing you the ball and stick models. So here you can see the mirror, and these are obviously enantiomers. Now, if you have a nucleophile come in, and do a backside attack, an SN2 reaction on this one, you'll get that product. If you have a nucleophile come in and do a backside attack on this molecule, you'll get that product. And so you can see, here you have a pair of reactants, and if they undergo the same reaction, you will have a pair of products, which are mirror images. This reaction demonstrates stereospecificity. So when you think of stereospecificity, think of this: a pair of reactants undergoing the same reaction to give a pair of products. And here this is a pair of enantiomers undergoing the same reaction to give a pair of enantiomers. Okay, a pair of stereoisomers giving a pair of stereoisomers in a reaction. Okay, so it's a pair leading to a pair. That demonstrates stereospecificity. And I don't think that the discussion in the textbook is clear at all. This is correct, and I think this is clear. I hope so. If it's not, you can ask me about it. So, more on hydroboration oxidation. It's stereospecific. Only syn addition occurs. This is coming out of your textbook. It is not stereospecific. It is stereoselective. Okay. So, and once again, so this is coming in. The hydroboration oxidation, it can come in from the top or it can come in from the bottom. Okay, because this is an alkene. And the fact that you get two different enantiomers out of it, that's totally irrelevant. Yes, you would get two different enantiomers, but you don't have the pair of reactants. Now, hydroboration oxidation. So, predict the products of this reaction. So, here you can see that you're going to have hydroboration. The boron is going to become attached at the less sterically hindered end. So obviously boron is going to become attached up here and hydrogen is going to go there. You could have the boron and hydrogen come from the top or come from behind. It can come from the front or from the back. And so if it comes from the front, the boron and hydrogen are going to be on this side of the molecule. If it comes from the back, boron and hydrogen will be on the other side, and then boron, by the hydrogen peroxide and sodium hydroxide, boron will be replaced with oxygen. So here boron is replaced with oxygen. And stereochemistry is retained when the boron is replaced by oxygen. And that is a really remarkable finding. So let's look at these. The interesting part, so what if you get, if you have hydroboration occurring from the top and from the bottom? Yes, you're going to have that occurring all the time. Anytime you have a planar reactant, that's what's going to happen. But notice here, you've got the methyl group sticking out. And here you've got the methyl group sticking out. And here you've got the methyl group sticking out. So which one of these do you think will predominate? So with this methyl group sticking out, and your hydroboration can occur from the top, or from the front, or from the back. Hydroboration can occur from the front or from the back. So if it occurs from the front, boron is going to have to form here, and it's going to bump into this methyl. And then the boron will be replaced with oxygen. So this is going to be your minor product because of this steric hindrance. Because this methyl is sticking out, you're going to have hydroboration occur more from the back side. Okay? Not exclusively, but the hydroboration occurring from the back side, and then boron will be replaced by oxygen on the back side. And then, of course, the hydrogen is there on the back side. And so this is going to be your major product. So you might want to go over that so that you will understand it. Now, go on to catalytic hydrogenation. Catalytic hydrogenation is simply the addition of H2 across the double bond. And there's a lot of reactions that will give catalytic hydrogenation. There are many metals here that are used: platinum, palladium, Raney nickel. There are many other metals that are used. Basically, if you see H2 and a metal, it's probably going to give you catalytic hydrogenation. It requires, a metal catalyst. Only syn addition is observed here. Yes, only syn addition. And so once again, it can occur from the front or it can occur from the back. And so this, I think that stating this over and over and over again I'm faithfully reproducing this from the book, but I don't think it's really necessary to keep saying that. Anytime you have a planar reactant or a planar intermediate, and a reagent is going to come in and react with it, it will be able to come in from the back and from the front, or from the top and the bottom. I mean, because it's planar, that's always going to happen. The point of having a catalyst is that it provides an alternative reaction route, an alternative reaction pathway. So without the catalyst, you're going to have a high energy of activation. If you have the catalyst, you're going to have a different pathway, and you're going to have a lower energy of activation. That's what is significant. So this sort of depicts what is happening in catalytic hydrogenation. So here's the metal. Okay, all of these dark gray marbles down here. And now you've got hydrogen. This was H2, H2, H2. And so H2 it's become absorbed onto the metal. And so it's just sitting there. And then the alkene comes down and it associates with the metal also. So the alkene comes down, the pi electrons are associated with the metal, and so it is sitting there, and it's sitting there next to the H2, and they just react. Okay, and so since they react, and they're right next to each other, they're going to react. So they're going to be sitting next to each other, and then they're going to react. Okay, and so when they react, the H2 is going to add from the same side of the molecule. And so that's why you're going to get syn addition, because the H2 is absorbed and the pi bond is absorbed, and they're next to each other, and so then they react. And so you're not going to have one of the hydrogens jump around to the other side of the molecule as the reaction takes place. And then when the reaction takes place, you have the deadsorption. So syn addition across the pi bond. And syn addition produces only one product, a meso compound, because this on this one, because you have a mirror plane. It's a symmetrical alkene. So now similarly, when you have Wilkinson's catalyst is not just a metal surface. Wilkinson's catalyst is this molecule. And so what happens, once again, is you have H2 reacting with the catalyst, and then you have the pi bond reacting with the catalyst, and the catalyst is holding all of these parts together, and then the or all of the reactants together, and then the H2 reacts with the pi bond, and it reacts from the same side. And so once again, it is syn addition. So it is syn addition, but it's a syn addition for a different reason. Okay, so what you have is you have the H2 is added onto this catalyst, and then you have the pi bond associated with the catalyst. And so when the hydrogen is added to the pi bond, the two hydrogens come in from the same side onto the double bond, because it's all, they're associated with the metal. So this is called Wilkinson's catalyst. Now notice this is triphenylphosphorus. So now let's think of, and this is more about the chiral centers, the generation of the chiral centers. I really don't think that has anything to do with the stereoselectivity of that reaction. So so when you have the three triphenylphosphine ligands, here, if you replace two of the phenyl groups with other groups. This is not like when you have an amine. When you have an amine, you would lose this stereochemistry. There's inversion. The nitrogen does not retain any stereochemistry. But here, the phosphorus will. And so you can have a chiral phosphorus compound where you would not be able to do that with nitrogen. And remember, nitrogen is just above phosphorus in the periodic table. You can do it with phosphorus, not with nitrogen. Okay, so here, this one is symmetrical. All three of the groups on phosphorus are the same. Here they are different, and it is possible to synthesize different chiralities in this. So it's possible to synthesize this molecule and the enantiomer and keep them separate, and they will retain their chirality. So that is remarkable. And so then whenever you effect that Wilkinson's reaction with this, you will generate chirality at that center. You add H2 across here, and this becomes a chiral center. And if you use that chiral catalyst, let's see, yeah. So in other words, instead of using triphenylphosphine, if you use this up here instead, if you replace these triphenylphosphines with this chiral group here, so if you would put this here, here, and here, and carry out the reaction with this version of Wilkinson's catalyst, then you can generate chirality in the product. And that is remarkable. That's surprising, and it's remarkable, and he shared a Nobel Prize for doing it. So I'm not certain that is anything that you would ever see on an exam, but it is important, and it's important to realize that those sorts of things can be done. And so this is another one that is somewhat similar. The person that shared the Nobel Prize, he used this catalyst that is somewhat similar to the previous catalyst. And again, I don't think that it's necessary that you memorize these things, but rather just remember that it's possible for this to happen. And so here, H2 was added across there using this chiral catalyst, and he was able to generate, get this one enantiomer with a 95% enantiomer excess, 95% EE. And so I don't think that it is necessarily so important for you to remember this specific result, except just to remember, the main thing is just to remember that these chiral catalysts do exist, have been used, and can generate chirality in a reaction where you wouldn't normally see it. That's what's the important thing to remember from this point. Halogenation. So halogenation is the addition of a dihalide across a double bond. Chlorine and bromine mostly are observed. Bromination is most common, I think, and it's a key step in the production of polyvinyl chloride, PVC. And so, but it's a very common reaction, and it's been studied a lot. Here, you get anti-addition in this reaction. And let's see, halogenation, the addition of I2 across, it does happen, but it's not practical. It happens so slowly, it's a poor reaction. And with F2, it's too violent, so you you're in danger of having explosions, and also it does other things. So here you're getting anti-addition. Anti-addition. And so you can think of it like this. The double bond approaches Br2, and so it's coming in. So here you can see the bromine, or you can think of the bromine as approaching the double bond. And so then the pair of electrons in the pi bond attack the one of the bromine atoms in the bromine molecule. And what happens is this is electron rich. And so as the bromine, the Br2 comes in, you have a high electron density. And so the electron density in the bromine-bromine bond moves to this end of the molecule. So that's what is meant when it is stated that bromine, molecular bromine, is polarizable. So the Br2 becomes polarized because the pair of electrons here come in and polarize Br2. So this end of Br2 is partially positive, this one is partially negative, and then the pair of electrons attacks bromine, and the bromide is displaced. And so, in some cases, if the carbocation that could be generated is extremely stable, it's believed that in some cases, there is actually a carbocation intermediate formed. But usually not. They have to be really stable situations. So for most cases, it would be incorrect to draw this intermediate. You would not have a carbocation intermediate unless it's an unusual situation where the carbocation is unusually stabilized. Okay, I don't want you to get confused here. So once again, look at this. So this is making the point again. The pair of electrons is polarizing Br2, coming in, attacking, bromide is leaving. And if you did have a free carbocation like this, where the bromine becomes attached to just one of the carbons, and the other carbon was just bearing a positive charge, you could have addition from the top or the bottom. So you would get syn addition or anti-addition. And that is not observed, except in really unusual situations. Like if you, let me go back over here. Like let's say that you had a couple of phenols on here. A phenyl group here and a phenyl group here that would really stabilize that carbocation. Then it's observed. But in most cases, it is improper to draw this intermediate as a carbocation like this. So this is, and they're making the point that it's known that this is wrong because you don't see both syn addition and anti-addition. You only see anti-addition. So now let's look at why you only see anti-addition. So once again, you have the double bond coming in, polarizing the bromine, and you have then attack on bromine, and the pair of electrons moves back in and attacks the other end of the double bond, and you have simultaneous loss of bromide. And so now what you have is this bromine bearing a positive charge, and it's divalent. Now, bromine normally is only monovalent. Monovalent, only bonded to one thing, one other atom. Here it's bonded to two other atoms. So this is a bromonium ion. Okay, this is a bromonium ion. There's a lot of evidence for this bromonium ion. Okay, and the same thing can happen with chlorine, and there it's called a chloronium ion. Okay, and this is another one of those onium ions that I was just talking about. Increase the valence by 1 and put a positive charge on it. Bromonium. Okay, so this is a three-centered intermediate. Three-centered intermediate. You have a three-membered ring here. Three-centered intermediate. And then the bromide, which was lost up here, comes back in and it attacks. Well, it's not going to attack from up here because this side of the molecule is blocked. So it comes in and attacks from the bottom. The pair of electrons moves out on the bromine. So one bromine atom is on one side and the other bromine atom is on the other side. So it's anti-addition because the bromines are attached on opposite sides of the ring. So this is like backside attack, and there's the product. Anti-addition, bromonium ion. Okay, so halogenation is stereospecific. So if you use cis-2-butene, you will get one product, and it's enantiomer. If you use trans, you get the other product, and it's enantiomer. But here the two enantiomers happen to be the same thing, so it's a meso compound. But in this case, you have a pair of stereoisomers leading to a pair of stereoisomeric results. So the P is for stereospecific, okay? P, it's stereospecific. Okay, so this is another example of stereospecificity. A pair leading to a pair under the same reaction conditions. Now, halohydrin formation. What you have here is halohydrin. So you have a halogen and water. So this is reacting with a halogen. So you saw how we reacted to get the bromonium ion. So this is with Br2, and the pair of electrons, reacts and forms the bromonium ion, and then you have water in there. So oxygen now is the nucleophile, and it comes in and does a backside attack. Oxygen becomes attached to one side of the molecule. Bromine becomes attached to the other side of the molecule. So this is really the same mechanism as addition of bromine, and so it has the same anti-addition. So what happens is you have some bromine and a lot more water. And so instead of having Br minus attached here, you have water attached. That's the nucleophile. Okay, so let's see if there's anything here. This gives a little more information, but so water removes the proton. Here's your product. You can have the same thing happen. So this is a bromohydrin. This is a chlorohydrin. This reaction will go through the chloronium ion. Okay, so it's the analogous mechanism. So the regiochemistry is that, so you will have bromine attack, and then you have water come in from the backside attack. The bromine goes to the terminal carbon. The water goes to the internal carbon, and that might seem strange, so let's look at why. So what happens is when you have the positive charge on the bromine up here, so this is pulling electron density off of both carbons over here. You've got electron withdrawal. And so you're going to have more electron density pulled off of this carbon that is a tertiary carbon than over here. So you've got more positive charge in this region. So oxygen is electron rich. So this, and it's bearing a partial negative. So this partial negative is attracted to that partial positive. And that's what happens here. So you have the oxygen-carbon bond. So the bromine is pulling more electron density off of the tertiary carbon than the primary carbon. And so the oxygen, with its electron density, partial negative, is attracted to the partial positive. And so that's why you have attack by oxygen at the more highly substituted oxygen and carbon. And so that's why you have this regiochemistry. Okay? That's why you have this regiochemistry. And that will be important. You'll want to remember it. So, let's see. I think this just depicts what I just finished saying. So here's the transition state where you've got the carbon-bromine bond partially broken, the carbon-oxygen bond partially formed, just like an SN2 reaction. It is an SN2 reaction. Okay, so that takes care of a lot more of our reactions. We've just got a couple of more oxidation reactions, and that's what we will consider. That's what we'll discuss in the next video.